All right, this is the sample test for functions trigonometry for the first half of chapter 3, which is exponentials and logarithms. We want to be sure that we're using no calculator for this part because there will be no calculator when you take it in class. All right, let's get started. Number 2 says write in exponential form. So this is logarithmic form. We have to remember that whatever the base of the logarithm is, in this case is 7, will be the base of our exponential. Whatever used to be inside the logarithm, so in this case the x, is now on the other side, no longer with the base. And whatever used to be by itself, the answer to the logarithm, is really the exponent of the base. So that's just memorizing how to convert back and forth between log and exponential form. All right, number 2 asks you to find the domain of f of x equals log of 3 minus 2x. So the base of this logarithm is 10, but that doesn't really matter. What really matters is we can't take the log of a negative number. So whatever is inside of our logarithm is going to have to be greater than 0. I can solve this equation. I would just move the 2x to the right side. Then I would divide both sides by 2, and I'd have 3 halves is greater than x, or x is less than 3 halves. In this case, we like to plug in negatives because putting a negative in here will be multiplied by the negative of the subtraction, and then I'll really have a positive evaluation in my logarithm. You can also think of it like the negative on the inside here will flip our graph left and right. So instead of going to the right, this graph will go to the left, and our domain is now going to be a less than. Number 2, find the inverse of 4 to the x. I show inverse with a little -1 in the exponent. The easiest thing really for this is just to realize the opposite of an exponential is a log. So the opposite of a 4 to the x is a log base 4 of x. If we wanted to do this one algebraically, my other option would be to switch x and y. So I would have x equals 4 to the y if I switch x and y from the original problem. And then in order to get this y by itself, how do I get y out of an exponent? Well, I convert to logarithmic form. So the base of my log would be 4 because that was the base of the exponential. The y used to be in the exponent, so now it's over by itself. And the x, which used to be by itself, is now with the base over inside the logarithm. Same thing either way. Find the inverse for number 4 of log of x. We need to realize that that is a common log, so it is a base 10. So when we find our inverse would be a 10 to the x. Again, we could do it the same way by switching x and y, or just by realizing that they're inverses. All right, let's scroll down a little here. For number 5, we are finding the inverse of 2e to the x plus 3. If I'm using my method of just thinking of opposites, I know that the opposite of this parent function, the opposite of an e to the x function, would be a natural log of x function. Then I need to take care of doing the opposite of the other operations. I had an addition on the inside. The plus 3 was added with the x, so the opposite of adding 3 inside would be subtracting 3 outside, and that will be on the end. If this is going to have an inside, you're going to have to put it right here around the x, if we want to parentheses. So we also had that 2 out in front. This 2 was multiplied. It's on the outside because it's not in the exponent. So the opposite of multiplying by 2 on the outside is dividing by 2 on the inside, and that would be inside of our logarithm. So again, this is my inverse. My other option for this would have been to switch x and y and then get the new y by itself, but that one's going to be a little more complicated. All right, let's go on to number 6. Okay, I just gave myself some axes there to make this a little easier to see. On this, we're supposed to graph by creating a table of values, state the domain range, and the equation of the asymptotes. So the first function I'm graphing right here is y equals 3 to the x. They've given me a spot for a table down here below. So 3 to the 0 is 1, 3 to the first is 3, 3 to the second is 9, and 3 to the third is 27. You know, I'd start at 0. So 3 to the -1, the negative tells me to push that 3 down to the bottom of a fraction, which is 1/3. 3 to the -2 would then be 1/9, and 3 to the -3 would be 1/27. So I'm going to plot these points over 0 up 1, over 1 up 3 for my origin, over 2 up 9, or I could be going to the left. These guys get close to my axis. It's kind of hard to draw, so I just want to be sure I have my tail going to the left. I have an arrow on the end. I'm shooting up to the right, and I have my arrow on the end. And I've also shown that this function has a horizontal asymptote. The equation of that asymptote is y equals 0 because it's on the x-axis. I also want to state the domain and range. Since I go forever from left to right, my domain is all real numbers, or I could write that as negative infinity to infinity. Doesn't matter to me which way you write it, either the negative infinity to infinity or the fancy r. The range is from 0 up, so in interval notation, that's from 0 to infinity, both in parentheses. Or in set notation with a greater than symbol, I could say y is greater than 0. Realize there's no equal to on that range because I don't touch the asymptote. All right, on to number 7. We are going to graph by transformation now. So I want to think about where I'm moving. I have this plus 3 on the end. It's on the outside. So my whole graph is going to be moved up 3. And this is sort of like my new anchor point, my new origin for this problem. I also have a negative out in front, which is going to flip me vertical. So instead of going up, my graph is going to flip, and it's actually going to be a decreasing function. So wherever my anchor point was, I had an asymptote there. And then my shape, my normal shape for 3 to the x would be to go over 0 up 1, but instead I'll go down 1. My normal shape would be to go over 1 up 3, instead I'll go down 3. My normal shape would be to say 3 squared was 9, so I'm going to go down 9 instead. And my negative exponents, those just got close to my asymptote over here, and they're hard to plot nicer points. I connect with a nice smooth curve. I've got arrows on both ends, and my asymptote is nicely shown with a dashed line. The domain on this guy is still from negative infinity to infinity because it goes left and right. The range is now going down from positive 3, so my range in interval notation is from negative infinity to 3, or you could say y is less than 3 if you're writing it with inequality symbols. The asymptote was at y is equal to 3. The x-intercept of this function was up here where I touched the x-axis, which was at 1, 0. The y-intercept for this function was where I touched the y-axis, which was at 0, 2. We also have a little end behavior information right here. As x approaches infinity, that's the right side of the graph. On the right side of the graph, my graph was headed downward, so my graph approaches negative infinity. As x approaches negative infinity, that's the left side of my graph. So if I'm over here in this left arrow, my y's were leveling out there, and they were getting closer and closer to y equals 3. All right, number 8 is another transformation. In this one, we haven't moved at all, so we're still anchored at the origin. So our asymptote is still going to be right here on the x-axis, which is at y equals 0. I'll write that down now. What is happening with this function, I have a negative up here on the inside. So instead of starting out and increasing, our graph is going to flip, and this is going to be exponential decay. We also have a 1/2 out in front, which is a vertical shrinker because it's on the outside. So I'm only going to go up half as tall as I would normally go up. All right, so let's think of our points. My normal point would be to go over 0 up 1, but instead I'm only going to go up half as much. So my y-intercept there is 1/2. Normally I would go 1 to the right up 3, but instead of going right, I'm going to go to the left, and instead of going up 3, I'm only going half as much. So I'm going 1 to the left, up 1.5. For my next point, normally I would go over 2 up 9, but instead I'm going to go 2 to the left, and instead of going up 9, I'm going to go up 4.5, because that's half of 9. When I start taking half of my little fractions for this tail, they're really close to the asymptote, but I'm just going to draw them on there. I wonder if 3 would fit on the graph too. I didn't try to plot that one. But let's think about what would happen. If I did 3 to the 3rd power, that would equal 27. And then when I take half of 27, that's 13.5. So it looks like I'm not going to get another point on this graph. I'm just going to keep finishing that up there. All right, the domain here was from negative infinity to infinity because I go left and right forever. My range was greater than 0. So I can write that either way because I went up. Is the function strictly increasing or strictly decreasing? This would be decreasing, because as I go from left to right, the function is falling. The slope is negative that whole time. All right, let's turn the page. All right, on number 9, I'm on to logarithm graphs. This is a log base 3. So essentially, what I'm going to do is I'm going to take my 3 to the x function, and for my log base 3, I'm going to switch my input and my output because I have an inverse. So I'll start in the middle of my table, and normally my x would be 0, and 3 to the 0 would be 1, and I'm just going to write it backwards. So 3 to the first is 3, 3 to the second is 9, 3 to the third is 27. In the negative direction, 3 to the negative 1 is 1/3, 3 to the negative 2 is 1/9, and 3 to the negative 3 is 1/27. So I just wrote everything down in the opposite order, where my y is now my input and my x is my output from a 3 to the x. So when I graph this, what winds up happening is my old horizontal asymptote is now a vertical asymptote at x equals 0. Remember, you can't take the log of a negative number. All of these x values were always positive. So let's plot some more points on there. I've got 1, 0. I've got 3, 1. And I have 9, 2. I have 1/3 negative 1, and the tail down here is going close to the asymptote. My graph has arrows on both ends to show that it keeps going in both directions. But when I go to state my domain is limited for this one. I couldn't take the log of 0 or a negative, so my domain is just from 0 to infinity, or x is greater than 0, however you want to write that. My range, however, is now all reals, because the y's could be anything. My answer to a log could be positive or negative. As x approaches infinity, that would be the right side of the graph, or this right arrow over here. What is happening? The graph, or the y value, is approaching infinity. There is no left end behavior for this one. X can't approach negative infinity. But we do have a local behavior as x approaches 0, which was right down here in the tail of the asymptote. As I was getting closer and closer to 0, my y was headed down, so y was approaching negative infinity. Number 10, we have a transformation. In this one, I have a +2 on the inside, which is going to move me 2 to the left. I have a -3 on the outside, which is going to move me down 3. So if I go 2 to the left and down 3, this is my anchor point for my new graph. So I'm going to pretend that's my origin there, and in a log graph through the origin, I have my asymptote. It's vertical, so my asymptote is now at x equals -2, and my points were to go over 1 up 0, to go over 3 up 1, to go over 9 up 2, and then I got closer and closer to the asymptote over here in the tail. Okay. I have a domain here from -2 now to infinity, because I start at -2 and go to the right. My range is still all reals. And this function is strictly increasing. It's increasing from -2 to infinity, but that's everywhere in its entire graph. All right, the next bit is evaluating using the properties of logarithms. It says if the log exists, it is a single rational number. So that means we want to give nice simplified answers. So what is this asking? Log base 5 of 125. The question that's asking is 5 to what power gives me 125? Well, 125 is 5 to the 3rd power, so that means the answer to the logarithm is 3. Make sure you answer the question. You don't just leave the 3 in the little box. Okay, number 12, the log of 10,000. The base of this logarithm is 10 because it's a common logarithm. So this means 10 to what power is 10,000? Well, 10,000 has 4 zeros on it, so I would need my exponent to be a 4 for the 10. Number 13, 6 to what power gives me 6? Whenever these two numbers are the same, that means my exponent must be a 1. So the answer to log base 6 of 6 is 1. Number 14, 1/2 to what power gives me 16? I have two things going on here. I need to turn this 2 into a 16. The way I do that is by raising it to the 4th power. The other thing I need to do is bring the 2 from the bottom of the fraction up to the top. The way I take a reciprocal in there and flip a fraction is to put a negative in the exponent. So the answer is -4. Number 15 is the ln of the 5th root of e. So the base of this log is an e because it's a natural log. So I'm asking e to what power gives me 1/5 root of e. Well, I don't like that as a radical symbol there. I'd rather write that as the 1/5 power because it's the 5th root. So that means this is 1/5 is the answer to the logarithm. Number 16, 9 to what power gives me 3? Well, the square root of 9 is 3, and the square root is the 1/2 power, so that's the answer, 1/2. Number 7, 6 to what power gives me 1? Anything to the 0 power is equal to 1, so the answer is 0. Number 18, 2 to what power gives me 1/16? Again, I have two things going on here. In order to turn the 2 into a 16, I need the 4th power, and in order to bump the 2 to the bottom of a fraction, I need a -4. The last one, number 19, is the log of -5. We cannot take the log of a negative number. This means 10 to what power gives me -5. There's nothing I could put in this exponent that would ever turn the 10 negative, so this does not exist. All right, the last question asks, between which two integers does the log base 3 of 30 lie? Well, let's think, what is the log base 3 of 30? The log base 3 of 30 means 3 to what power gives me 30? Well, this is not something that's such a nice number. Let's see what I do know for 3 to the powers. I know 3 to the first is 3. I know 3 to the second is 9. I know 3 to the third is 27. I know 3 to the fourth is 81. So if I'm looking, 3 to what power gives me 30? Well, 3 to the third power gives me 27, and 3 to the fourth power gives me 81. So I need the power up here to be a little bigger than 3, like a 3.1-ish, something like that. In other words, my log base 3 of 30 is going to have to lie between 3 and 4. It'll be a 3 point something, so that it gives me a number between 27 and 81 when I'm doing my exponent there. Okay, now we're jumping over to the calculator part. We need to calculate the log base 3 of 218. So if I'm going to do that on a calculator that doesn't have a log base, I need to do the log of 218 divided by the log of 3. Remember, you do the log of what you're taking the log of divided by the log of the base. So be sure, if your calculator gives you parentheses, that you close them. Also, some of you guys have the pretty print calculators where you can hit your math or your option button and go to log base, and it will give you the little boxes that you fill in. If you have that kind of calculator, sorry I don't have it on the screen, then you can just fill in the 3 and the 218. So for mine, I need to do the log of 218 divided by the log of 3. And my answers are always going to be truncated to 4 places after the decimal. So I'm going to have 4.9011. That's just making sure you know how to find a log in your calculator. For 21 on, we're solving word problems. I'm supposed to show all equations used and give answers as sentence with units. In number 21, I have a savings account that earns 5.8% interest. It's compounded continuously. So that's our cue that we need to use A equals P e to the RT formula. We have an investor that is going to put $5,000 into his account. So $5,000 would be the principal or the initial amount. We're trying to look at what they have in the end. we have E. We had an interest rate of 5.8%. Our interest rate always has to go in as a decimal, so that's 0.058. And then we also have the question here, how much will they have after 20 years? So I'm putting 20 in for T for 20 years. So I want to go ahead and put this in my calculator. And as you're typing that, be sure that you have both the 0.058 and the 20 inside the exponent. And that gave me his final answer. I'm going to write this with a dollar symbol because it's money. $15,949.66. Remember, the bank, we could round that up to a 67 cents, but banks often don't round in our favor. So I'll just truncate. So for money, I'll go ahead and truncate to 2 places. For the other ones, I'm going to give 4 decimal places. All right, number 22. According to an advertisement in your collector's guide, a particular Star Trek trading card collection should increase at a fixed value of 10% annually. If you bought the $29.95 collection today, how much would it be worth in 15 years, according to the ad? So this is just like interest. You're gaining some money. You're gaining 10% annually. So $29.95 is your initial amount, and we're looking to see how much we have after 15 years. So our formula for compound interest is A equals P times 1 plus R over N to the NT. A is the amount at the end. That's what we're looking for. Our principal, our amount we start with, is $29.95. Our rate is 10% annually. As a decimal, that's 0.10 when we move the decimal over 2 places. This is annually, so that tells us our N is equal to 1. And I fill in N both down here on the bottom and up here in the exponent. And T is the time in years, which was 15 years. So I just need to type this in my calculator. So that gives me $125.10. 10%'s a lot of money to make, especially on something like a Star Trek card, so probably not all that realistic. But that's what the ad claims, so we're not necessarily going to believe that ad. All right, number 23. Let me scroll up here some to get the rest of the stuff on the page. 23. 30 years ago, 17 pounds of a radioactive element were buried in a toxic waste dump. The half-life of the element is 7 years. How much of the element is present today? So we're going to use our idea that the amount that we have at the end is equal to the amount we have at the beginning, and then we're going to put our rate in here since this is a half-life. That's going to be a half. And then up here in the exponent, we're just going to multiply by a half however many times this is going to repeat itself. So we got to think about that for a second. An amount at the end, we don't know. That's what we're looking for. We're starting with 17 pounds. So I'm going to put 17 as our initial amount. And we're trying to figure out how many times this process repeats. Well, if we started with 17 pounds and we took half of that, that would be 8.5 pounds. And how long did that take? That took 7 years to occur because the half-life of the element was 7 years. So if we're going to span over the course of 30 years, how many times are we going to repeat this process? We're going to repeat this process, whatever 30 divided by 7 is, so a little more than 4, because we repeat the process every 7 years. So let's go ahead and put this into our calculator. Again, make sure if you've got the 30 divided by 7 in your exponent that you have them both in parentheses or both up there in your calculator. And the answer that I get from that is 0.8716. My units for this were pounds, because that's what I started with. Now let's just see if this makes sense. Again, I started with 17. I'll just show my calculator. I started with 17. Whoops, that's 177. 17 divided in half. So that took 7 years. So after 14 years, after 21 years, after 28 years, so I need to go more than this, but not the full next half-life. So somewhere between 1.06 and 0.53, that means my answer makes sense in this situation. All right, number 24. When buying a $20,000 car, you have a choice of two finance options. Option A, the car manufacturer gives you a financing for a 5-year loan at 4.9% APR, and it's compounded monthly. Option B is the car manufacturer gives you $1,000, like there's a rebate. So if you're doing that, you're only going to have to finance $19,000, and then you're going to go to your bank and you're going to get a 5-year loan at 5.49% APR, and that's also compounded monthly. So how much total would you have to pay off with each option, and which financially is better? So let's start with option A. Both of these are interest formulas, so they're going to follow RA equals P1 plus R over N to the NT. And here's options A choice. Option A, we're starting out, we have to finance the whole car. So the principal of our loan, oops, I forgot to write down A equals. Get that back there. We've got A equals, we've got our $20,000 that we're going to loan. Our interest rate on this one was 4.9%, so as a decimal, that's 0.049. This is compounded monthly, so N is 12. And my loan is going to be for 5 years, so T is 5. And let's see what I have. So I typed all that in my calculator, and I have a $25,539.68. That's how much I would wind up paying off when I pay off this loan. So for option B, I'm getting a rebate of $1,000. So now my principal is only $19,000. But in this one, I have to go to the bank, and the bank sometimes gives me a higher interest rate. Depends. You have to shop for these things. I also have a compounded monthly, so my N is 12, same compounding. And I'm also going to do 5-year loan, so T is 5. So let's try this one on our calculator. So by putting $1,000 less into the loan, even though I have a higher interest rate, I still wind up paying less total for the car. So I would want to, here are my first two answers, sorry. There's how much I would pay off with each, and then which is a financially better option. It looks like option B is better. Okay, there we go. Let's go on to the next page. Okay, in this one I'm supposed to use the chart below from the Department of Health and Human Services, the National Center for Statistics, Health Statistics, to answer the following questions about the United States death rate from 1900 to 1995. So this was in the previous century. It says find an equation for the exponential regression of the death rate using x as the number of years since 1900. So in 1900, my years since 1900 were 0. In 1905, that was 5 years. In other words, what I'm doing here is I'm chopping off the 1900 when I type this into my calculator, because sometimes my calculator gets a little confused when I put in really big values of x and try to do the regression. What I'll do for you guys is I'll use my Casio right here when I do my regression, and then after that I will do the same thing again with all the keystrokes for the TI, but I don't want to do them at the same time because it might be too confusing. Okay, so I need to go into my statistics menu on my calculator, and I need to put these things in the list. My X list would be the year since 1900. So I'm going to pause the video while I type all those in. So I typed in all 20 data points getting up to 1995. And then I'm going to go over to list 2, and now I'm going to enter each of the death rates. So 17.2 was the death rate in 1900, and I'll pause the video while I do that again. So I have all of my data here up until 1995 again. I'm going to hit F1 to graph, and then my calculator should be set up. I'll check my F6, my setup real quick, is a scatter plot of list 1 and list 2. You usually don't have to change that because that's the default setting for the calculator, but I'll go ahead and hit graph 1, and I can see this looks pretty exponential because it's falling steeply and then flattening out. So in order to find the exponential regression, I hit F1 to calculate, and then I'm looking for exponential. That's not an answer choice, that's on this menu, so I hit F6 for more options, and exponential is F3. This point can be a step different depending on whether you have the calculator I have on screen or the one I have in class. If you have the calculator I have in class, at this point it gives you a choice to choose F1 or F2. We usually choose F2 because that's the same option as TI uses, but it doesn't really matter. It just matters whether you're having a base that is an E or whether you're coming up with the base as a variable. So my calculator only rates this way, so it would be y equals 14.8589 e to the, now my b is negative 6.79 times 10 to the negative third, and all of that is then times x. If you had used the F2 button on your calculator, you would have gotten the same coefficient, 14.8589, but your base instead would have been 0.9932, and then that decimal keeps going, but that's all I'm going to write down, to the x. Again, it doesn't matter which one you use, both are going to give you the same answers in the next step. Regardless of which one you use, you would hit F5 now to copy the equation. It takes you to the graph menu, and although you don't see it, if you hit the EXE button, it's going to paste it there. You can also hit the draw button and see how it goes through. So it looks like this is not really necessarily the perfect fit function, but it told us in the direction to use exponential, so that's what we're using here. All right, in number 26, I'm supposed to use the regression to predict the death rate in 2010. Well, in 2010, we would know what x is. X is the number of years since 1900, so that would be 110 years since 1900. So I have two options for this. I can go into my graph menu, and I could draw this. Now, if I draw this and I try to go to trace to see what happens when x is 110, my calculator is going to tell me, oh no, it does fit in mine. Sometimes it will say not found, and you might need to zoom out a bit if you're predicting beyond your window. But using this for x equals 110, regardless of which equation I used from number 25, I should have 7.0400 as my death rate. In number 27, it says, according to the regression, when would the death rate have been 11.1? Well, in this case, I know the death rate, which was the y value. So if the death rate is going to be 11.1%, the only place I can put in a y value in my calculator would be to come back here and put in a y2 as 11.1. I can then graph it, and I can go to gsolve to find the intersection, and that was at 42.9487, which is not an answer to when. My when would be in 1942. You could also justify calling that 1943. It's a good idea to give your answer with the 4 decimal places also, and then give the realistic rounded answer. Okay, so that's it for the test. Come in ready with any questions that you have and be good to go. If you want the TI version, I'm going to do that now. So if I'm using my TI, I need to hit the stat button to go into the statistics. I want to go to enter to edit my statistics. Now my calculator still has stuff in it from the last thing that was done, so I'm going to go up to L1 and I'm going to hit clear, enter, and it'll delete everything that's there. I'm also going to go ahead and delete L2 while I'm there. All right, so in L1 I need to enter the numbers from 0 to 95, and just like before, I'll pause the video while I do that. So I've entered all of my information in L1 from 0 to 95, and now I'm just going to over to L2, and I'm going to enter my death rates in there, starting with the 17. Whoops. Let's back up and call that 17.2. Again, I'll pause the video while I fix this. So I entered all my data in L2 here. Make sure you always wind up with the same number of things in list 1 and list 2, or this process isn't going to work out for you. So now I'm trying to find my equation, so I go under Stat, and now I need to hit the over button to calculate. Oh, let me graph this thing first. Sorry. I'm going to go into my y equals. I'm going to delete anything that's there. And what I want to do is I want to try and graph plot 1. So I'm deleting what's there. I'm going to go now to second stat plot. And for plot 1, I'm going to hit enter. And I want to turn plot 1 on. So I'm going to hit enter. Your calculator should be set up by default to be a scatter plot of list 1 and list 2. If it's not, you have to fix that. And now I'm ready to graph. On my TI, if I want to get this in the window, it's real important that I need to do a zoom stat, which is down at the bottom there, zoom 9, and I can see there are the points on my curve. I can confirm that everything looks normal. I can do an exponential regression now. So I'm going to go back to stat. I'm going to go over to calculate to find the regression. And then I'm going to scroll down because I'm looking for exponential regression, and that's 0, exponential regression. And I can just hit enter at this point. Depending on which calculator model you have, it may ask you for some different things at that point, and you just have to scroll down and be sure you've filled in that information. You can see that the function I just got was the same as the function that I had told you would come up if you used the Casio's a times b to the x method. So I write that down. Now I want to do my predictions. In order to do my predictions on the calculator, I need to get this equation into my y equals. If I go to y equals, I don't want to just type it in with the 4 decimal places, or that's going to lose a lot of detail. So what I want to do is I want to go to vars, and then it's a statistic variable that I'm looking for. So I go to statistics, and then I scroll over twice to get over to equations, and number 1 is RegEQ for regression equation, and if I hit that, it will paste my equation. So you can do the same type of thing on different models of TI. The other thing, if you had the pretty print screen, on some of your calculators, it came up and it asked you where you wanted to store the regression, and it gave you the option of like Y1 or Y2. You could do that as well. So let me graph this, and we can see there's my scatter plot, and there's my curve going through it. If you want to get the curve only, so you want to get the scatter plot out of the way, you can go back to y equals and go up to plot 1 and hit enter, and that will turn that off. See, now it's not highlighted. It doesn't matter. You can do this either way. So I'm going to go to graph, and I want to calculate the death rate in 2010. So I need to put in x equals 2010. The easiest way to do that is go to trace, and if I type in 110, I don't know if it's going to fit in the window or not. It's saying not found. What I need to do then is I need to go to my window, and I need to make my window a little bigger. I'll make it 120. That should be plenty big. And then I can go to trace again. So I go to trace and I type in 110. The other thing I could have done is gone to the table and plugged it in there instead. But this worked, and you can see this calculator is giving me 7.0623. Okay. My Casio had given me 7.0400. Number 27 asks, according to the regression, when would the death rate have been 11.1? So in order to do that, I need to put in y is 11.1. So the only place I can put in y equals 11.1 is in my y equals. So I go back, and in y2 here, I'm going to put in 11.1. I'm going to graph, and I can see where they cross is where the death rate is 11.1%. So I'm going to go to second, calculate the intersection, and on this one I have to move close to where they cross and hit enter for the first curve, hit enter for the second curve, and hit enter for the guess, and it tells me the intersection is 41.9773 on this calculator. Oops, I forgot my 41. So that would be in about 1942, which is the same thing I got when I did my Casio before, which is what's up here on the screen. Again, it's a good idea to give 4 places after the decimal and the rounded answer. All right, let me know if you have any questions next time. Thanks.